A very good evening to one and all present here. A warm welcome to each and everyone who have gathered here or assembled here for this event. This is the SSE E talk series, and this is the 6th talk of the series. I am Dr. Deepak, Associate Dean, International Affairs, Saveetha School of Engineering. Will be hosting the session. I would like to thank our director, madam, for madam's motivation, guidance, and support in organizing this event and conducting the event. I would also extend my gratitude to our principal sir and vice principal sir for their kind support. Today we have with us Dr. Weiping Wu, professor from City University of London. Dr. Weiping Wu is the George Daniel Lecturer in the Department of Electrical and Electronics Engineering at City University of London, United Kingdom. He was a research associate at University of Cambridge from 2010 to 2013. In 2013, he was appointed as a research fellow in the Optoelectronics Research Center, University of Southampton. He has published more than 50 papers with total citations over 3,700 and an H index of 31, which is very high. And let me take the privilege in welcoming Dr. Weiping Wu. Please, over to you, Professor. Thank you.
Thank you very much. Hello, everyone. And it's a great honor to be here. And thanks a lot for the invitation. And today I will give my talk with the title of Functional and 2D Materials for the Next Generation of Electronics. And my name is Weiping Wu. I'm the George Daniel Lecturer at the City University of London in the United Kingdom. So first, before my talk, I'll briefly introduce myself. So I came to England about 10 years ago as a research associate at the University of Cambridge, working on 2D materials and graphene. Then after a couple of years, I joined ORC at the Southampton University, working on photonics, lasers, metamaterials, and so on. So since 2015, I've been appointed as the George Daniel Lecturer at City University of London. And at the same time, I became the chairman of a Chinese group of Society of Chemical Industry, SCI. So nowadays, everyone on this planet enjoys the benefits and the convenience offered by the electronics. Even now, we are using internet and using cameras and using our PC, laptop, and smartphones on this webinar. Actually, the core technology is based on semiconducting materials, mainly using silicon. At the same time, some other compound semiconductors has been also utilized, such as gallium nitride, silicon carbide, and gallium arsenide, and so on. Although the huge success on this electronics since about half century ago, when the microelectronics developed after the Second World War, following the invention of a transistor device at Bell's laboratory. There are several major challenges, such as the high cost of the semiconducting materials and processes, and poor flexibility, and limited to small areas. So for certain areas or applications, scientists and researchers have been seeking for new materials and new technology towards the flexible and large area electronics. So nowadays, many of these type of technologies has benefited us through this new technology, such as the touch screens, the electronic papers, and the photovoltaic devices, and the sensors, as well as smarter textile devices for wearable electronics, and some radio frequency devices such as RFID and the microwave and the wireless sensor devices, and so on. So if we looking or review this famous kind of technology roadmap by the industry leading company Intel Corporation on these transistor technologies. So the transistor technologies starting to scale down since the 1960s, actually. So there's a famous law called the Moore's law, saying that the transistor device will be smaller and smaller, while the density of the device will be much larger. So since 2007, then the transistors gate or channel devices have been scaling down from 15 nanometers to the current dimension about 10 nanometers or 7 nanometers, which is the state of the art. And right now, the industry is still pushing very hard towards the even smaller channel lengths, but it's almost hitting this kind of physical limit. And we are nowadays seeing a very slow kind of changing on our transistor, like for mobile phones or CPUs for these PCs, rather than other directions or technology like high K or this a low power designs of these chips is much being studied or kind of implemented. Then, but beyond that, there are other technologies arising, like the quantum devices, carbon nanotubes, 2D material like graphene. So these technology would be quite promising in the next decades or in the next few decades, and would find some of their applications in electronics. So today I'm talking about two main aspects, which is the functional material for electronics and 2D material for electronics. I will start by quote this the famous Nobel Prize for chemistry in 2000, which is awarded to Professor Alan J. Hager and Professor Alan G. McDermott and Professor Hideki Sarakawa on their discovery and development of conducting polymers. So this conducting polymer has been regarded as a new class of material, and then in earlier years, since 1980s actually, so the main focus has been focusing on developing or studying the conductive polymers. But in the recent 10 years, then the major focus and efforts have been shifted towards the semiconducting organic and polymer materials. So these polymer and organic materials has been developed based on the principle of conjugated bonds of carbons. So then these conjugated structures has a characteristics of delocalization of charge carriers. So therefore, similar to inorganic semiconductor like silicon, then this organic material can form this kind of energy gap, and just like inorganic semiconductors. So then in this organic functional materials, then we call them as a HOMO and the LUMO levels correspond to the valence band and the conduction band. So during my PhD, since my PhD, I've been doing my research on materials and organic field effect transistors. And actually, when we're looking at transistors, so these transistors can be classified as a top contact and the bottom contact. And if we go beyond organic transistors, actually this nano transistor device can utilize a wide range of materials, from inorganic to nanocarbon materials to organic semiconductors and so compound semiconductors. Then the associated layers like these insulating layers and electrodes can utilize in either organic or polymeric material or inorganic like dielectrics, or and for electrodes, then we can use in metals or carbon material or printed like metallic structures, as well as the conjugated polymeric materials to form these contacts with semiconducting material. So other materials associated to this technology include this substrate or this encapsulation layers and connection materials and so on. So to develop these conjugated molecules with charge carrier conducting capability, or to form this semiconducting organic and functional materials, two main methods have been utilized. They are classified as this coupling organic chemical reaction. The first one is called Suzuki coupling. So the second method is called the steel coupling. So among these fields, then we are very interested in new chemistry and new synthesis methods and to develop novel materials or structures. So during my PhD, I've been discovered hundreds of materials and tested their properties and build up this optoelectronic devices based on these conjugated small molecules of polymers. And I published a review paper at the Chemical Society Reviews, and I summarized these small molecular polymers, 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional organic functional materials. So there are some kind of slides that kind of showing you some of my research works on developing organic field effect transistors, organic memory devices, and organic photodetectors, as well as organic nanowire transistors. So first, I will introduce briefly about the development of the organic p-type materials. So on the left hand of the slides, we can see that there are small molecules which shows quite a strong pi-pi stacking. And this type of material on this on the left left above of this slide is showing a bio-TTF, which is a classical kind of charge transfer salt small molecule. So we have redesigned this molecule and has extended this pi structure, and we found a very high mobility, which indicates the strong pi pi-stacking inside the molecule from this single crystalline packing. So the mobility by solution process about 15 years ago, it has been reached towards the range of 10 to -2 centimeter square per volt second, and it was comparable to silicon. And nowadays, the mobility of solution process small molecule is much higher. It's reaching the mobility of amorphous silicon. And for polymeric semiconducting materials, we can also develop p-type and n-type or bipolar polymeric material. And but among this journey of this discovery of studying this material, in particular for this TTF-based semiconducting material, and we made some achievement, and but at the same time we found some problems for this material. There are several challenges on developing this class of material. The first challenge is its low mobility, and the second challenge is low on-off ratio and poor air stability. So in my PhD thesis, I proposed several solutions towards this quite difficult challenges. So firstly, I introduced this blending these small molecules with polymeric material. In this case, it would be a material called polymeric material called PVK, and could be some insulating material like PMA or PS polystyrene. And in this, by this simple approach, blending or compositing approach, forming these semiconducting channel of these organic transistors, this output characteristics can be can show this kind of sortation behavior. Also, the off ratio has been improved. So the second approach is using the molecular engineering. So using our synthetic approach, then in this way, then we can synthesize these molecules from this by tailoring their chemical structures. So then we actually learned quite a lot from this classical molecule. Then, for instance, this perylene bismuth, it's a famous kind of red dye that is pioneered by the German corporation BASF for industrialization. So in daily life, a lot of red dyes that we are being using actually is this type of perylene bismuth dye. So learning from this molecular structure, we have designed this kind of this molecular one and compound 1, compound 2 with this electron withdrawal functional groups and this long chain. So we grow these single crystals of these new compounds, and then have formed the thin films by thermal vacuum deposition. Then these new materials are very different from the BTTF I showed in the previous slides. They showed a much higher mobility, which is about an order of magnitude higher, and a much higher off ratio, about 10 to 6 to 10 to 8, and then which means that our molecular design approach has been very successful. But from a molecular or theoretical point of view, then actually the HOMO level and the compound 1 and 2 has been much much kind of reduced towards minus 5.46 EV to minus 0.42 EV. So then beyond this, then we have also designed a lot of molecules on P-type polymeric semiconducting material and N-type polymeric semiconducting material, as well as n-bipolar semiconducting materials. So then in particular, like this kind of a polymer with fused ring structures show the enhanced mobility. And this kind of metallic containing polymers has also shown very, very encouraging results. Then, besides my research on this polymeric and small molecular semiconducting material, I also pushed the kind of dimension limit for these transistor devices by considering the very fundamental limit by bridging the two electrodes with a molecular dimension. So pushing the effort towards the molecular and nano electronics. So as you can see, then there are methods using carbon nanotube as electrodes or as gold as electrodes to assemble a single molecular at the electrodes. So you can test this type of single molecular devices using this type of very special single molecular device architecture. So then another dimension of this research is to grow this single crystal using this organic material. So in my PhD period, I have grown a wide range of single crystals by a very special kind of vacuum transporter process. So a range of kind of very beautiful kind of single crystal has been grown successfully from this molecule with 3 benzene rings to 4 benzene rings and 5 benzene rings. They are called as the N-rings and the terrins and the pentensine. And so then actually during the growth also I observed some very interesting phenomena. Then this type of pentensine actually will result into some black kind of a black or more insoluble structures. They tend out to be as this type of a kind of graphene-like structure. So this leads me to pursue my research in the area of 2D material. Actually, when we review back this history on carbon material, we can see that in around soon after the Nobel Prize for chemistry, then there are some kind of photos about the C60, C70, as well as C1 million, actually, which means that the carbon material is made of about 1 million of carbon. So actually, this can be regarded as this kind of graphene structure. But about 20 years ago, nobody actually had thought about this graphene structure. But until the Manchester Nobel Prize winners group, they have isolated or produced this graphene material by a very simple method by using a Scotch tape and graphite single crystal, which is a similar material has been produced to produce a pencil codes. So this carbon material, this graphene, single layer graphene, is important for several reasons. The first reason is it's a template for carbon-based material. As you can see, a graphene single sheets can lead towards the fluorine and these nanotubes and this graphite. And secondly, it has an excellent physical property like this mechanical property and this electronic property and thermal property. And thirdly, it has shown very interesting physics like a spin, quantum Hall effect and a spin dependent transportation, which can lead towards very fundamental physical study and these kind of spin-based electronic devices. So that's why the Nobel Prize in Physics has been awarded to Professor Andrew Kim and Professor Konstantin Novosov. Then actually, this is a very groundbreaking experiments regarding the two-dimensional materials of graphene. And besides this electron property, then actually the graphene is a very interesting material because it observes only 2% to 2.3% of the white light. So this slide showing you an example of how this graphene single layer or few layer graphene can be made. So using Scotch tape, using graphite. So using a very simple method by exfoliating the tape several times, then expose the surface of the graphite, then you attach to the silicon substrate, then actually you can find some single layer or few layer graphene under the microscope. So this is as simple as a few layer graphene can be made. However, there are challenges on this method because you can't make a very large area or very high quality, uniform graphene using this method, although this quality of sample are the best. So there are other methods being proposed. At Cambridge University, we have been working with a company Extron grow this graphene using this like a semiconducting clean room facility called Black Magic. And then using this facility, we are able to grow graphene at the 8-inch wafer scale by the CVD process. So by growing the CVD graphene on the wafer, we are able to build this so-called artificial fuel graphene using a newly developed process at the University of Cambridge by repeating transfer this single layer graphene grow on this copper silicon dioxide silicon wafer. So by repeating the process, it gives us a very special opportunity stacking this graphene towards the bilayer graphene, tri-layer graphene, 4-layer graphene, and a 5-layer graphene. So I've collaborated with Professor Yang Hao at the Queen Mary University, London, and Professor Bill Muir, who was the head of the department at the electronic division at the Cambridge University, and build some very interesting sample towards the radio frequency application and test them using the micro cavity measurement. So using this non-contact measurement, we can determine this sheet resistance without destroying the sample. So similarly, recently I've extended this piece of measurement further by developing this nanocarbon cavity at much smaller scale in about 200 nanometers and metal materials at about 500 nanometers of semiconductor materials. So we tested these RF cavities using this optical absorption techniques as well as Raman spectroscopy to confirm the successful conformation of this bilayer, 3-layer, 4-layer, 5-layer of graphene. And in addition, we have determined their sheet resistance and show a very interesting trend of the reduction of the sheet resistance when the layers of graphene increased. So this offers us a new approach to build this low resistance electronic device, as well as to build this high performance radio frequency devices. So beyond these vacuum processes, or some of the graphene samples and can be prepared by a range of methods. But the most important methods, including the silicon carbide method and this chemical synthetic method. So we can also using chemical and a very simple kind of physical based method by using graphite as starting material, then put the graphite in the liquid or water, then using ultrasonic as a power source to prepare or to exfoliate the graphene into the solution. So in a simple or typical process, we put the graphite powder into the solvent, then we ultrasonic with a very simple facility, the ultrasonic benchtop machine. Then after centrifuge, then we can actually separate the fuel graphene and the exfoliated graphene. Then the inks the graphene inks can be produced. So when I just arrived at the University of Cambridge, I can make only about 1 mil or 2 mil of graphene, typically by 2 or 3 days. Then gradually I scale up the process, then can make about 20 mil of graphene. Then I can make a liter scale of graphene. And nowadays, then this process can make a ton scale, even much larger scale graphene. So this method is very useful and powerful, and then we can produce graphene using a different source of 2D material like a polonitride or MOS2 or WS2, and give us very high quality samples of these 2D materials. Then using these things, then we can print, we can like pattern or deposit these materials on this flexible substrate. Then among various methods for solution process, we are using this inkjet printing as the method to deposit these materials for electronic and photonic devices. So then graphene can be successfully formulated for inkjet printing purposes. Then this slide shows you that this process of the ink, these ink drops like jetted from the nozzles, and then they can be successfully kind of jetted on the surface. So there are kind of a lot of technical challenges on this printing process itself, on including the formulation of these inks and this substrate kind of wettability, and also this stability of these ink drops. So nevertheless, after a lot of trying, we successfully injected this kind of graphene stripes on the substrate by supported by the ozone treatment of this kind of substrate and this self-assembled monolayer on the substrate. So this morphology or this quality of the graphene injected of kind of stripes quality has enhanced. That's it forms these conductive channels, and then we typically get about 80 micron of this spots, and then by overlapping these spots, we can form these stripes of graphene to be connected by the golden electrodes. Then this can allow us to fabricate field effect transistors, and the mobility of this device is about 95, about 100. But due to the zero band gap of graphene material, we have very low kind of on-off ratio. Then by using a semiconducting polymer of polysilicon, which is PQT12, when we composite graphene ink with this PQT12, then we can enhance the mobility towards we can enhance the mobility of PQT12, but also enhance the on-off ratio of graphene transistors. Although the mobility is not as high as the graphene transistor itself, but overall it's a very high performance of inkjet printed or solution processed field effect transistor devices. So then after that, then I've done a lot of work on pushing this technology towards industry by industrialized the process on using graphite as material, then produce the very low cost graphene ink. Then also there are other methods to produce like a few layer or single layer graphene using graphene oxide. But however, the graphene oxide has some challenges for the purpose of high conductive graphene. So because this type of precursor of the GO is very defective due to the oxidation process used to produce GO, then also it requires a reduction process. So therefore, then the literature reported the results in the literature reported using GO or RGO as a conductive for layer for transparent conductors that has very high sheet resistance around a kilo ohm square and with poor transparency. So therefore, based on the graphene ink, has been developed this new class material by attaching metallic nanoparticles to the graphene flakes. It's so-called metallic decorated graphene. So I have been using a institute like a chemical reduction processes and attaching these silver nanoparticles on top of this graphene flakes. Therefore, then these defects at the agents can be kind of repaired, and these metallic nanoparticles can be attached then to form this kind of interconnection or bridges between these flakes, so that the conductivity can be greatly enhanced. So therefore, I'm using another printing process, so-called a roll-to-roll process, to printing this graphene large area transparent electrodes. Then they show very low sheet resistance, around 50 ohm per square, using silver, and it's about 200 ohm per square using gold. Then this result has led to very successful large area like smart window devices and display devices, and our samples have been exhibited at the Royal Society exhibition in 2011 and the Graphene 2012 International Conference at Brussels impression. Then these early demos of this industrial kind of prototype of products then has led to the successful successful application towards the Graphene EU flagship projects, and which allows the scientists to carry out more research using this 1 billion euro for 10 years. And then we have built this kind of transparent conductors using graphene and the smart windows. So we segregated the polymer dispersed liquid crystal between these two transparent conductor layers, and by applying a voltage, so this transparency status of this device can switch between on and off. It relies on very similar principle as a liquid crystal display, but it shows but it's covers large area and it doesn't have a pixel. But this type of device is particularly important and useful for a kind of electrical modulated optical window, or that we can control this kind of sunshine or lights transparency kind of intensity. Therefore, you can using them as a windows, or you can using them as energy manipulating devices for kind of sustainable green buildings. So this table summarizes the performance of this kind of transparent conductors. Then actually, our solution process, the graphene transparent conductors are comparable to the performance of the CVD graphene, which actually consume a lot of copper resources and rely on very expensive equipment. So also this like flexibility test showing that after bending, repeating bending, this graphene electrodes are flexible and they show a very kind of small amount of increasement on this resistance, only 10%, while for IT, which is Indian tin oxide, they show about 250 times of this increasement on this resistance, and even it may induce kind of failures when used as a transparent conductors. So, which means that we have provided a new solution for this next generation of flexible electrodes for flexible and wearable electronic devices. So recently, I've been doing some work on produce these three-dimensional kind of graphene or carbon materials for sustainable kind of energy harvest of solar light and wind energy. Then using this solar energy and wind energy, we could actually convert the seawater into drinkable fresh water. And this piece of work has been published as a front cover paper in the journal Advanced Functional Material. And our porous carbon material is very special because it provides kind of mechanical properties. So this bulk carbon material can show kind of very high compressive strength and bending strength. Then more recently, I've been using a very common polymeric material, which is PVC, contain chlorine items towards the production or synthesis of sustainable porous carbon material by the idea of carbon material derived from conjugated polymer. So using PVC, we could using a very simple mechanical chemical approach by grinding with a solvent, and then the chlorine items can be partially removed from this polymeric chain of PVC, forming this conjugated bonds, which you can tell from the color changing of this sample from whitish to yellowish to brown or blackish. So then after thermal treatment, we can produce this porous carbon material with very high surface area. Then we can produce this this kind of also solar steam devices using this technique. So also, if we review back the different type of carbon material from three-dimensional, two-dimensional, then to one-dimensional, and to zero-dimensional, we can see that these materials have been very interesting trends on this dimensional distributions. Then also, then actually we could actually consider the combination any 2 or 3 or more than these numbers of materials of the different dimensions. So therefore, I had an idea on combining 2-dimensional material with a 1-dimensional material. So this is a recent paper about the combining 2-dimensional graphene and 1-dimensional carbon fiber, and then by electrode deposition method, then we form this type of composite material using this concept and successfully prepared this composite material. And by this approach, this a very high performance material boosts this seawater evaporation rate dramatically, and we could get an ultra high performance of this seawater steam generation about with evaporation rate about 45 kilograms per meter per hour, which means that you can essentially get about 45 kg or kilogram of water if we have 1 square meter of this material in an hour. So this is a breakthrough in this field, and we also had successfully demonstrated low voltage of this device, which is very important to utilize this kind of renewable energy of wind or solar cells. And from this infrared image, you can see that this temperature goes up very quickly from room temperature towards 300 ish. The highest temperature we can reach is about 389 centigrade. So then after energy harvest, there are actually a lot of amazing technology like electrical vehicles and also flexible electronic devices that demands the energy storage or this type of wearable solutions and so on. So we are using these same carbon materials for this kind of electronic storage purpose. So still using this 1-dimensional and 2-dimensional kind of material compositing approach. And I've been using this 1-dimensional tungsten disulfide nanotubes with this graphene as a new electrode material for these batteries, and show amazing kind of energy storage performance. And then during my research, I've been using various carbon material and tested them at the standard electrochemistry cell, and found that interestingly this like a more functionalized carbon material actually showing a better performance compared to the graphite electrodes. So it's lead us to seeking new carbon material with nitrogen element doping and unique shapes like bowl shapes and this type of 3-dimensional shapes towards the supercapacitors. Then this piece of this slide showing four different kind of hollow carbon structures with different kind of geometry. So these hollow carbon particles have been synthesized by silica template method. So by using this the material, we can using this unique shaped carbon material as the electrodes for supercapacitors. And the supercapacitors show a very impressive kind of performance regarding the device parameters. And then we also kind of further actually filled the inorganic material like MOS2 and metal oxides inside this hollow carbon structure. So to summarize my talk today, I'm presenting these kind of optoelectronics using this functional organic material and the 2D materials. And actually, this is a very attractive research field and also promise a lot of applications and from these materials and processing devices and systems. So towards that end, a lot of effort should be made to the functional materials themselves, then optoelectronic devices, as well as their application in areas like the energy sensors and healthcare and so on. So by working or collaborating and also working with industry people, it's very encouraging that we could find a very near kind of industrial larger scale applications. So this slide is showing you some example about the kind of various new applications of functional material and the 2D material for electronic devices, ranging from these electrodes and the MEMS and the FET and the nano antennas and sensors. So then in those further, like once these devices have been successfully developed and produced in larger scale, then this technology can be applied in practical world for this healthcare, sports, wearable electronic devices, automatic and transportation, electrical vehicles, and these portable consumer electronics, and smart homes, and so on. So I think, personally believe this the future of these optoelectronic sensors with the functional material and 2D material are bright, and there would be a lot of new discoveries and new technologies that appear in the near future. So I would finally like to thank my collaborators and my supervisors, and Professor Andrew Ferrari and Professor Dabin Chu at the University of Cambridge, and Professor David Payne and Professor Nikolai Joseph at Southampton University, and my supervisor at China Academic Sciences, Professor Dao Benchu and Professor Yingqi Liu, and my collaborator at Shanghai Jiaotong University, Professor Pingyuan Zhao, Dr. Fenhua Liu, Li Jian Wang, and Professor Robert Bradley at the University of Oxford. And I also would like to thank the SSE Innovator UK and the GCR from the UK, and some industry and charity support from Samsung and George Dennis Trust, and the International Union of Pure and Applied Chemistry and the Society of Chemical Industry. Thank you very much.
Yeah, thank you very much, Professor. It was really an enlightening talk. You have highlighted about functional materials, graphene synthesis process. Then you also talked about optoelectronic devices, the future of optoelectronic devices, and it was very interesting, and a lot of prospects, future prospects is there for us all to work on that, to do and carry out a lot of research in that. Thank you very much. Now let me make the floor open. Like participants, if you have queries, you can ask one by one, please.
Okay, thank you.
Yeah. Please ask one by one.
Hello, Professor. This is Dr. Cyril from EC department. Thank you for an excellent and interesting talk, sir. I have two questions. One is it possible to connect self-assembled monolayer, or like RS, like silane molecule or pentacene molecule as a channel between source and drain for a FET device?
Yeah, so I can answer this question first, then I will answer later the second question. So firstly, like the self-monolayer of molecules, they tend to be an insulating material. It's not say you can't getting a conducting layer, but it's quite difficult to getting a conductive or a semiconducting cell modeling monolayer. But if you achieve so, or you can even find a few like literature reporting these type of devices, then it's possible, yes, it's possible to contact with the electrodes and form devices. And in my opinion, maybe the main challenge of this type of device is because the fact that it's monolayer of organic material, so the stability at the electronic active layer is not very high. So maybe there's a lot of effort to pushing this structure of this self-assembled monolayer to allow the charge carriers to transport. For pentacene, it's a small molecule, so it will form crystalline structure in lattice. So it's already more difficult to get a monolayer of the molecule at pentacene. Then of course, if you can functionalize the pentacene, then you may have a chance to to form electrodes. The most kind of frontier kind of achievement in this field is the IBM Corporation. Actually, they imaged a single pentacene molecule by AFM, atomic force microscope. But still, at the present, it's technically it's very challenging to put down two electrodes at this molecular scale, which is talking about the sub-nanometer scale. but I think it's a very powerful approach in the field of the single molecular electronics. Thank you.
Thank you, Professor. And one more question. How do we achieve deposition of molar layer of graphene? Deposition of monolayer of graphene.
Okay, so for monolayer graphene, as I explained, the most famous and the typical method is using Scotch tape. So using a natural graphite, a piece of natural graphite from the mine or synthetic graphite flake, then you using your Scotch tape manually. You paste it, then you release it. You paste it, release it. Then you expose this fresh surface of graphite. Then you can transfer the bulk graphite onto a silicon dioxide surface. Then after you pull up your tape, then you can get some sort of monolayer and a multi-layer few layer graphene mixture on the substrate. But this monolayer is very small. Say this and for solution process and for CVD. And so for CVD, if you're using the copper the catalysis on the substrate and using the right condition to grow the graphene, it's easier to get a monolayer graphene. But this method, using this method, the graphene is attached on the metallic copper, so you need a transfer process to get the monolayer graphene. So for other methods, maybe like reduce the GO is possible, but for printing, it's quite difficult to get a monolayer graphene. But we can only say that in my method, for the mechanical exfoliation of graphene, it's a mixture of single layer, bilayer, tri-layer, or few layer graphene after centrifuge. Thank you.
Thank you, Professor.
Yeah. Any more questions from the participants?
So can you hear me?
Yeah. Please go ahead. Please go ahead.
Okay, sir. I'm Karthika from University of Madras. That was really a valuable talk, sir. And also, I need to thank the organization for giving such intellectual lecture organization. So thank you, sir. So apart from that, my question is on carbon material. So my field of work is on X-ray detection, sir. I was using an interdigited electrode board. So when we are using a carbon material, as we all know, that was very good optoelectronic material. So what problem I'm facing is we are making this carbon paste using a polymer. Will that give any effect while doing an electronic detecting process? Sir? Will that affect my photocurrent characteristics?
I know I understand the process, but can you repeat what's the main problem again?
Yeah, sure. So it's about an X-ray sensing detector material. So for that purpose, I'm using a carbon material, carbon paste, like carbon nanotube. So when it was added with a polymer, I'm getting a reduction in the photocurrent characteristics. So what is that issue, sir? Because of polymer or a carbon material as an issue?
Yeah. So yeah, I see. I think it could be it must be a combination of this type of reduction effects or negative effects. Maybe actually, firstly, using carbon with a polymer, naturally you will reduce the conductivity significantly. Then this has been well understood in the literature by conducting carbon-based like composites. You can find a lot of literature and so on. So you can optimize and push it. But it's difficult because if you are introducing insulating polymer, your conductivity will reaching a certain value on which you can't increase or improve much. Then secondly, providing your device structure actually using carbon as a material, then it must have certain work function. So maybe the interface between the semiconducting layer or your active material layer and this carbon paste layer is another key issue. So to clarify these two effects, it's the best to first to using maybe a pure carbon-based kind of ink. Then you can tell whether the performance is improved or not. Then to tell whether it's effective work function, or you can deposit by different materials with different work function. Metallic electrode with different work function. And for polymer-based paste, if you can't get rid of polymer, maybe you can consider some post-treatment, like a thermal treatment, to push your kind of performance further. Thank you.
Okay, sir. Thank you, sir. That was very clear. Thank you, sir.
Yeah.
Thank you, Kartika. Then any other questions from the audience, like participants? We can take one more question. Anybody else? Anybody else? Okay. If there are no further questions, let us all thank the speaker. Thank you very much, Professor. It was really a wonderful talk. Like only one quick question popping up in my mind. Like you talked about functionalization. Even I worked a lot in functionalization of materials. But at this stage, what is the like stage we are in? Like how much we are clear about functionalization of materials? Whether we were in a position to achieve various functionalizations accurately with full percentage, like whether it is possible right now.
Yeah, I can answer the question in maybe in two aspects. Firstly, from the chemist point of view, maybe chemists design the molecular and synthesizer on design, saying you can control at the molecular or atomic level precisely. But the challenge is that when you functionalize a molecular or polymer, then yes, you can control that structure very precisely. But the bulk format of this material, it includes another level of packing, similar to these pretense four-layer structures and so on. So even though the same kind of structure, maybe you can expecting very different behavior. Maybe it completely go beyond your original design or functionalization. So it's difficult to fully control. But sometimes when you think, especially like optical property nowadays, is very like OLED material is very well understood, and you can more or less sort of predict its structure. Also, for small molecular, from quantum chemistry point of view, then you can precisely predict its physical performance, like band gap and this type of property. But still, because for small molecular, it may crystallize in very different way. And for polymer, it's a mixture of materials, so it's difficult to precisely to functionalize it. Then in regard to the functionalization of a bulk material like oxide surface or nanomaterial or carbon material, porous carbon material, again, these are more complicated system, more practical thing with defects or with a lot of kind of pores and so on. So this type of degree of controllability is still quite challenging. But for certain material like carbon material, there are known chemistry on certain attaching organic functional group like COOH group or OH group. At that level, the chemistry is kind of well understood. But beyond that, more complicated level of functionalization is still quite challenging. Some of the are not quite clear. Thank you.
Thank you. Thank you very much, Professor. It was really enlightening, and my special thanks to you for accepting immediately the offer and giving a talk to our students and faculty members. I would also extend my thank to our Director Madam for this opportunity, and also Principal Sir, Vice Principal for guiding me in all the way. Thank you everyone for joining. And also I'd like to thank Dr. Radhika Bhaskar and Dr. Hariharan for their technical and other support.
Hello, sir.
Yes.
Yeah, only one question, sir. Last question.
Yeah,
one question. Can I ask?
Please.
Okay.
Yeah, please.
Okay.
So
in solar
cell fabrication, can we use carbon as a counter electrode?
Could you repeat your question?
Sorry. In solar cell fabrication, can we use carbon as a counter electrode?
Okay.
If used,
yes.
The efficiency will affect or not?
So again, carbon is an amazing material because it's conductive, so it sort of can partially replace certain metallic or oxides conducting material for many electronic or optical devices, including solar cell. The answer is yes. But for certain devices like a photodetector or solar cell, then if you're replacing the standard electrodes with a new material, the chances is very high that you are compromise your performance, which is a main focus or main purpose of for researchers for industry people to pursue. So in a word, a simple replacement using carbon is usually decorate your device performance, but you can optimize, or you can even if you're lucky or you're good at it, then you can enhance the performance. But that would be very important kind of achievement. But on the other hand, for solar cell, for counter electrodes, for like a DSSC, then actually it's a catalytic process. So a pure carbon like graphite is not going to be a very good choice. But if you're using a functionalized carbon using atomic like doping, like nitrogen, oxygen, and so on, maybe it will show some performance. Then if it's more advanced kind of design of this type of counter electrode, maybe the performance would be even comparable to this standard, like a kind of standard very expensive metallic electrodes. But then again, if you are using like a so the answer is it's not that simply say yes you can replace it. It's more to do with the detailed scenario of the device structure of your device. So the best way to prove it is to fabricate the device, have a try and test the device performance. Thank you.
Thank you, sir.
Hope this answers the question, Mr. Raj Verman. Thank you very much. Thank you, Professor. Thank you very much for your wonderful talk. Thank you. Thank you everyone for joining the event.
It's my pleasure, and thank you very much for your invitation too.
Thank you, Professor Dr. Weiping Wu. Thank you very much. Good day to you. Thank you.
Thank you. Okay.
Bye.
Okay, bye. Thank you. Bye-bye.
Bye.